我写给你让你做。之前没有做啊，前面有做好，这边做。今天就一张就可以吗？就看一下这边，就看一下这个。
I'm the reporter of Team I'm going to report the problem 7 ruler tunnel. This is our outline. The first part is introduction of the problem, and the second part is the theoretical model, and the third part is experiment and result. The final part is conclusion. The first part is introduction. This is the problem statement. Two rulers are tightly held against each other. A round projectile is inserted between them close to one of their ends. When extra force is exerted on the surface of the rulers, the projectile is ejected at high speed. Investigate this effect and the parameters that affect ejection speed. This is a demonstrating video. And after we know the problem statement, there are some main points for we to focus on. The first one is when will the projectile eject? The second one is what are the parameters that affect ejection speed. And the first one is how to make the ejection speed larger. This is a phenomenon that we observed during our experiment. So, when we want to eject a ball, the first step is the applied force. We have to increase the applied force on the ruler, and then when the applied force increase, the angle between two rulers will also increase. And when the angle reaches critical angle, the force forward will be bigger than the frictional force. Thus, the ball starts to move. And because the coefficient of kinetic friction usually smaller than coefficient of static friction, the ball starts to accelerate. And the elastic potential energy of the ruler is converted into the kinetic energy of the ball. So the ball ejects out. This is a phenomenon that we observe. This is a VT graph and AT graph during the full ejecting period. As you can see, the ball starts to move at this moment and then it accelerates soon. And as for the AT graph, the ball starts to accelerate at this moment and the acceleration soon gets very big. And the acceleration decreases because of the resistance. The next part is the theoretical model. The first theory is for a bending ruler. For a ruler length L, I apply force at KL. There is a theory called uniformly beam theory like this. The M here is bending moment. It stands for the internal force in the ruler. And the EY is Young's modulus. The I is the second moment of area. It's properties for the cross section. For example, for a rectangular cross section, the I is like this. And with this formula, we can derive two formulas. The first one is for the distance that the ruler bends. It's like this. And the second one is the radius of curvature at the KL. And this is a quantitative analysis for a ball that it starts to move. These are the normal force and the components, and the red arrows are the frictional force. So when the force forward is bigger than the force backward, or in this analysis, the tangent half of theta is bigger than the coefficient of friction, the ball will start to move. And this part of theory continue the last part. So in this analysis, we can know the phi1 plus phi2 is equal to half of theta. And with uniformly beam theory, we can know the phi1 should be like this, and the phi2 is just arctangent r divided by L. So combine the theory that we talked about. When the ball ejects, tangent half of theta must be bigger than coefficient of friction. So we can know the critical force when the ball starts to move. And with this equation that I mentioned before, we can know the integration of FDY from 0 to the critical force. And this is the energy that I input into the ruler with applying force. And because the elastic potential energy is converted into kinetic energy of the ball, so we can know the velocity of the ball. And after the calculate, the velocity is like this, where the critical force is like this. But this theory has some limitations. The first one is that coefficient of friction is not a constant. We do experiments that we change the normal force, and then we measure the coefficient of friction for each normal force. As you can see, the coefficient of friction is not a constant when a normal force changes. And the second limitation is that we didn't consider energy loss in our theory. The first one is that because I use my hand to apply force in the experiment, and my hand cannot apply a quasi-static force, so that may cause some errors. The final one is the uneven friction on the ruler. Because there are scales on the ruler, the scales may cause bigger coefficient of friction, so that may also cause error. Next part is experiment and results. The first experiment is about the bending ruler. This is the setup for the experiment 1. We hang a weight under the ruler at a certain point, and then we take a photo of a bending ruler and then use tracker to get the radius of curvature at a hanging point. These are the variables for experiment 1. The operational variables are the ruler length L, the proportional constant K in this picture, and the hanging weight W. And the dependent variable we want to know is the radius of curvature at the hanging point R. This is the result for the experiment 1. The left picture shows the relationship between W and the reciprocal of R under a different L. As you can see, the W is almost proportional to the reciprocal of R. And I put the slope of the trend line for each L in this graph, and I will explain the result later. And the next result is the relationship between W and the reciprocal of R under different K. The W is almost proportional to the reciprocal of R under different K, and I also put the slope under different K in this picture. So after we get the result, we have to compare it with my theory. With the theory of the radius of curvature, we can know that the slope of the trend line must be this, or the EI, which is a material property, must be this. Because we use the same ruler for each experiment, so the EI must be a constant. So we calculate EI for each result, and then compare it with the standard deviation. The standard deviation for experiment of K is 0.02, and the sigma of the L is the 0.007. The sigma is small, so that proves our theory is generally correct. The next experiment is about the ball speed. This is the setup of our experiment. I apply force by my hand, and I use high-speed camera to record the ball ejecting process, and finally I use tracker to measure the max speed during the fourth period. These are the variables for the experiment 2. The operation variables are ruler length L, proportional constant K in this picture, and the projectile diameter R, and the projectile mass N. And the dependent variables are its projectile max speed V max. So this is the result for the experiment 2. The left picture shows the relationship between V max and L. And the red point is the theory prediction, the blue point is the experiment result. And the right picture shows the relationship between V max and K. And also the red point is the theory prediction, the blue point is the experiment result. There are some deviations because of errors such as I didn't consider energy loss in my theory. I use these two formulas to get the theory prediction. The next part is the part 2 of the experiment 2. Because it's hard to change the ball's diameter and mass, so I use PVC pipe instead. These are PVC pipe of different diameters, and these are PVC pipe of different mass. I use clay to fix the mass in this and change the mass in this. These are the results for the experiment 2, part 2. The left picture shows the relationship between Vmax and R, and you can see if the R is bigger, the Vmax will be smaller. And the right picture shows the relationship between Vmax and the mass. And if the mass is bigger, the Vmax will be smaller. The final part is conclusion. The first conclusion is about phenomena. If we want to eject a ball, first we have to make the angle between two rulers reach critical angle. And then the ball starts to move, thus the elastic potential energy is converted into the kinetic energy of the ball. And the ball ejects at high speed. And for the parameters, if the L is bigger, the Vmax will be smaller. If the K is bigger, the Vmax will also be smaller. And if the R, the diameter and the mass are bigger, the Vmax will also be smaller. And for the theory part, if we derive the theory at the theory part, and after it checked in the experiment, we can know that the theory is generally correct. Okay, thank you for listening.
Okay. Question for the opponent.
Do you use hand? Do you use hand to give the force?
Yes.
So can you make sure it's all the same force at the same?
No, but I always try to use the smallest force.
Obviously not accurate. Do you talk about force?
No.
No, you don't talk about force. Okay. Do you think the energy Do you think the energy didn't lost?
Sure, energy was lost, but I didn't consider it in the theory because the coefficient of friction is not a constant.
It's not a constant. Can you turn to page 23? Why is the left graph? Why is these two linear so different?
Mostly because the energy loss and the energy loss under different L is different.
So the difference is so big, and you said it's okay with the energy loss.
It's lost because the energy loss.
Can you turn to page 17? What is the W?
W is the hanging weight that I hang under the ruler.
Okay, and what is the R?
R is the
radius?
R is the radius of curvature at the hanging point.
Okay. And can you make sure every time your hand, when your hand gives it force, is it always vertical to the ruler?
Yes.
Yes. Well, how do you measure?
I didn't measure, but I always use the smallest force, and I increase my force slowly.
Okay. Okay. So you have 3 minutes to prepare. Time for comment to present. Good afternoon, everyone. I'm the opponent of this ruler cannon. Today I'm talking about ruler cannon.
statement. And their main focus is when it ejects and the parameter of speed. Theory. They use the Euler-Bernoulli theory and the coefficient of kinetic. Setup. They use a ruler and they use ruler and to use a ball, and they use hand, which is obviously not accurate enough. And they said about it. He tries to use hand, but I want to talk about this later. Experiment and data. Their parameter is the radius and mass. Pros and suggestions. Pros is that they have good parameters, which is the mass and the radius, and they have a lot of charts. Suggestions. I think they use hand is not accurate, which we will discuss about it later. And he said about nothing about the force, and the lack of the parameter of the mass of the ball, which I suggest they can consider it about. And if the ruler is parallel. Okay, let's move on to the discussion part. So, do you consider the mass of the ball?
Sure. I do an experiment about that, and I also consider it in theory. This graph is the Vmax and
Is it the same material of the ball and the ruler?
for sure not.
Huh?
I use table tennis ball and I use metal ruler. And when I want to change the diameters and the mass, I use PVC pipe.
So you use two kinds of pipe and the same ball, with the same ball, just the mass.
No, I put this pipe instead of the ball here.
Now why do you want to put that?
Because it's difficult to change the diameter of a ball.
Okay. So do you think that the energy didn't lost? Like what I previously said, because
I didn't consider it in the theory because the coefficient of friction under different normal force is not a constant, so it's difficult to calculate the energy loss. But it does happen in the experiment.
Is it related to the angle of the ruler?
Sorry, what do you mean?
When the ball is ejected, is it related to the ruler's angle?
Actually, I use critical angle to analyze that whether the ball will move. And the ball will move when the angle reaches the critical angle.
Okay. Oh, so is your ruler parallel? Because like if it's like a different.
I put it like this. This way.
Oh, you mean you put on the table?
Yes.
You put on the table. Okay. Oh, do you calculate the friction of the? Do you calculate the friction?
That cannot be calculated, but I measure
No, but I said, but you think about it. You can, if it's bigger than the biggest friction, then you can let it eject. So if you make some experiments, then you can know what is the maximum of the friction, and then so that you can know the biggest friction.
The friction is not a constant during the full ejecting process. cannot calculate it with theory or with experiment result.
You mean why this is not a constant? Is it? I mean, is it the same? If it is the different mass of the ball is not the constant.
The normal force.
The normal force.
The normal. The normal force is between the ruler and the ball.
Do you calculate the force the force?
Do you mean the force I apply on it?
No, the left one.
The normal force?
Yes, the normal force. Or it's not. It cannot be calculated by.
It can be calculated by if I know the force I apply on the ruler, and then I can calculate the normal force.
Oh, can you no? But can you calculate the force by some I suggest you can use a machine or something which is
for example,
have a stable force.
For example, I do experiment 1. When I have different weight, means different force, then I can know how the ruler bends. So, because I record the video during the ejection, so I can see how the ruler bends, then I will know how much does I apply the force.
Okay, so do you record the velocity by that camera?
Yes.
Okay, so how do you track it? Use tracker?
Yes.
Is your trackers track in the middle, or you use it automatically? Track it
Sorry, what do you mean?
Like tracker, it can track by your hand, track manually and track automatically.
Because it moves so fast, so I track by hand.
Okay. Is it always do you always track in the middle?
Yes.
Do you calculate the acceleration of the ball? Acceleration.
Because let me show you. Because the acceleration is a little bit irregular, so I prefer to measure the velocity.
And why do you think it's uncertain?
Because of the errors, and also because there are scales on the ruler, and that cause uneven friction.
Oh, so you just try two materials of the ruler, right?
Of the projectile.
Project.
I use the same ruler for all experiments.
Okay, we hear again.
I use the same ruler for all the experiments.
But you talked about the Young's molecule, so I think I suggest you can use another or maybe 2 to 3 materials 2 or 3 materials of ruler to.
Yeah, that will be a that will maybe I can do it in the future.
Okay. So what kind of material would you use in the future?
Maybe plastic or wood.
Is the ball eject vertically? Like you use it on the table, right?
Yes.
But if you take it vertical, like on the table, and like maybe because you use hand, and maybe one kind of force will be bigger, and then it may eject from another direction.
Actually, the ball moves for the same direction. For all experiments is move this way.
Can you repeat that video again? Because I think that because we cannot use our eyes to make sure it's completely vertical. Like if there's a straight line.
So maybe I can put an axis here.
Yes.
And that it will be more clear.
Okay, it will be clear.
Okay.
Do you think what's the difference between, you said you need to use wood and plastic, and what do you think of the difference between these two, like not the Young's but the potential energy?
The most difference is the Young's modulus, and also the coefficient of friction will be different.
Will the ball spin?
Time is up, so time for review. For opponent to summarize.
We talked about my 2 minutes short questions, like the energy loss, and the reporter shows the decline of the charge, so he knows the loss of the energy, and as to the hand he didn't show another clearer, better methods, and I suggest that they can use a machine or something, give it accurate force, and even vertically, which is a better experiment method. And we talk about more other kinds of materials that can be used in this experiment. And I think the Young is important.
Okay, so time is up. Reviewer can ask questions.
Okay, hello everyone. I'm the reviewer from TYPT, and the first question I want to ask the reporter in the page 10. So which part is L?
Like from the contact point to from the contact point between the ball and the ruler to the contact point between 2 rulers.
Okay, and And the second question is page 12. So you see that the different normal force will cause the different friction coefficient?
Yes.
Okay, and how about the
Can you repeat your question?
different normal force will cause the different friction coefficient?
Yes.
Yes. Okay. And about the page 16. What the KL means?
KL means the position that I apply the force or hang the weight.
And why you?
Okay. K is a proportional constant, the proportion between this distance and this distance.
Okay, so this is not the linear line. KL is not linear line.
What?
Just it's not a straight forward.
It is straight when where is no force. It will be straight.
And also you use you put the force equal to that straight.
Yes.
Okay, and first and page 25. What do you think about your air bodies? So big?
I think the main problem is because if the R is too small, I have to apply the force until the two ruler is contact at the position that I apply the force, and the projectile will eject at this moment at a super high speed. So the error during this condition will be bigger.
Okay, and from the opponent, do you think what parameters affect the ejection speed most?
I think it's the mass and the Young's model.
Okay, and what about the supporter?
I think it's the force I applied and the position that I applied the force.
Okay, and so and about page 6. 6. And yes, and I think you put the weight not at the middle part of the ruler. Do you think will affect your result?
Actually, I use theory for the condition that I apply force at KL.
Okay, time is up. So time for review and prepare.
Hello everyone, I'm the reviewer from Team Bernoulli, and I'm here to review number 7, ruler cannon. And two rulers are tightly held against each other. A round projectile is inserted between them close to one of their ends. When extra force is inserted on the surface of the rulers, the projectile is ejected at a high speed. So So investigate its effect and the parameters that affect ejection speed. And a summary of the report includes in energy transform and elastic force and Young's modulus and Euler-Bernoulli beam theory. And about the experiment, he used two identical rulers and ball and bending rulers and pipe. And about his experiment parameters, he do the ball velocity and diameter and mass. And about the strength, he used complete quantitative phenomena explanation and also use a good force analysis. And to my suggestion is that he can show his experiment video and to see how fast the ball ejection. And about the unsuitable fitting line, he could maybe do more fitness and a lack of explain about experiment data. And the suggestion and the strength of the opponent is that he explains some detailed point of the experiment and also he can tell the mistake from the report. And to my suggestion is that he can ask the question from the report and also ask more about the theory in the report. And also he can ask more about deviation between theory and data. I think in the discussion, the missed point is that feature of bending situation, an energy transform mechanism, friction coefficient, and definition of Young's modulus. And about the theory discussion, first, the opponent asked that energy was lost and wrote to say in theory, and I think he can follow it from friction. And second is to consider energy loss, and he said also in the theory can see it, and I think it needs to be considered. And third is angle important. And about the experiment, he using hand to do the experiment, and reporters say no, he tried his best to use the smallest force. But I think he could analyze the effect of using hands. And the second is why not using ball? And he said hard to change diameter of ball and maintaining same weight. But I think I agree with the reporter. And also third is to calculate the friction. And he said not a constant. And I think maybe friction coefficient won't change because of the normal force. So I think maybe okay. And to my question is why the friction coefficient will change, and it's like balls will change. But I think it depends on the material of ball and the ruler, so maybe the normal force won't affect the friction coefficient. Okay. And about what is the meaning of KL, and he said it's a straight line when it has no force put on it. But I think he can show the definition of what more clear. And about second is why the error bar is so big. And he said R, maybe he used it to do an experiment and R is too small, but I think he can need to show the data why the R will affect the error bar. And third is what parameters affect the most. And his reporter said force applied, and the opponent also said force applied and Young's modulus. So I think maybe the friction force between the ball and the ruler is the most influensive, because if your friction force is too small, if you put the biggest force, and then it will soon very fast to slip out. So the ejection speed won't very fast. So if the friction force is very big, and then you need to put the more force and to let it eject out. So maybe the friction force is the most important part of the phenomenon. And that's all my review. Thank you.
Okay. So time for the concluding remark.
So the concluding remark. The first is the ejection speed is decided by the elastic potential energy of the ruler, because the kinetic energy of the ball is from the elastic potential energy of the ruler. And then we can use Euler-Bernoulli beam theory to predict the energy in a bending ruler. And then the critical moment is decided by the coefficient of friction, but the coefficient of friction is not a constant when the normal force changes. And the fourth is about the suggestions. We should add the access in the experience setup video that will make the video more clear. And then we should control the force. Maybe we could use another better equipment instead of the hand to apply more stable force. Okay, this is the concluding remark. Thank you.
Okay, so time for jury to ask questions.
How did you measure the coefficient of friction?
I use the board. Actually, I cut the ball in half, and I use a ruler under the ball. So the way I measure the coefficient of friction is to see the tangent theta when the ball starts to move. And I add things in the ball so to change the normal force.
Could you write down the equation you use for deriving coefficient of friction? Which equation did you use?
I didn't use any equation to describe the coefficient of friction. I just measure and get the data.
Well, how did you get it? How did you measure it? So you measure the theta, right?
Yes.
The angle theta.
Yes.
The angle doesn't equal to the coefficient of friction.
The tangent, when the ball starts to move, the tangent theta at this moment.
What's the relation between the angle?
Tangent theta is equal to the coefficient of static friction.
You know, angle theta doesn't have any dimension. Coefficient of friction does have a dimension. It's equal to, I'm sorry, you got that. Am I right? Okay. Okay.
So any other questions?
There are two types of motion of the projectile. One is the linear motion, one is the rotational motion, right?
Yes.
Okay, can you visually compare the energy of the rotational motion and the translational motion?
Because I control the two rulers are symmetrical in my own experiment, so the force from each the ruler is the same, so there will be no torque. So the ball doesn't rotate that much.
So from your video, you can use the quality of the
Video. It rotates forward because the friction of the table.
and how are you tuned?
I think the rotation is because the ball and the ruler's friction is too small, so maybe it would slip up. So maybe the force, if the two sides of friction force is not the same.
You use hand and it's really hard to make sure it's all the same. Like even the tiny changes can make big difference.
Thank you.
Any other questions? Yes.
I think you are correct on that, but actually my question was the coefficient of friction shouldn't depend on the mass you put into the wall. So I'm just curious why the coefficient of friction changes.
This is explanation I found on the internet. For this part, because this is a surface of a ball, it actually has some roots on the surface, irregular roots, and it's soft. So when the normal force is bigger, the root part will go into it and then becomes smoother. So the coefficient of friction will be smaller in this part when the normal force is bigger. But when the force is big enough, the initial, the ball is contact with the ruler, and the actual contact area in this part is smaller than the actual contact area in this part. And because in this part of the coefficient of friction, when the normal force is bigger, the actual contact area between the ball and the ruler will get much bigger, so the coefficient of friction will be bigger. And for the final part, the coefficient of friction starts to decrease, mostly because the materials in the plastic ball release when the pressure is too big, because the coefficient of friction starts to decrease.
Okay, so it's about time to take the score. So for the reporter, 4, 6, 6, 8, 6. So for the opponent, 4, 4, 5, 5, 4. So for the reviewers, 6, 7, 6, 7, 6. Okay, so we close this session. Let's have another 15 minutes